Hi. So in this next example, we have a more of an algebraic equation with a radical and a linear term, yet the process doesn't change. So the methods will never change, just problems do, but we still are going to do the algebra part first, and then first derivative stuff second, and second derivative stuff last. So again, algebra stuff gives us this and first derivative gives us this, and second derivative gives us these pieces. So we'll just do step by step. So let's go ahead and look at this for the domain. Now we do know that the domain of x is all real numbers, but the derivative of a even square root, the radicand has to be positive or zero. So even though, and then we can just use our algebra skills. Even though x is all real numbers, right? Square root of x, so here's 0, is only here and positive, right? So we do the overlap only. So we know that the domain can include 0 and then all the way out to positive infinity. Intercepts is, again, when x and y are 0. So if I go ahead and rewrite what y equals down here, the first thing we could always do, the easiest, is the y-intercept is when x is equal to 0. We easily see when x is equal to 0 that the whole thing annihilates to 0. So you do have a y-intercept of 0, 0. For x-intercepts, that's when you let y equal to 0. So if 0 is equal to 2 square root x minus x, then we would have to go ahead and find those x values. Well, we do know one of them is already here because that's the origin, right? So we'll go ahead and just solve for x. Let's move x onto the left side, and we get x equals 2 square root x. And this is like a little old square root trick, right? Square root property trick. You can square each side and you get x squared equals 4x, right? So kind of like that. I put it in red because it's like, mental math. And then at this point, I would go ahead and just be very careful here and not reduce anything by an x, because that's a variable and that can include 0 from our domain. We don't ever want to divide by 0. So maybe let's move 4x also to the left and then factor a GCF of x minus 4. X times x minus 4 is equal to 0. And now we can see the other intercepts. We already knew x equals 0 was 1 from that y-intercept, but now we see x equal 4 is also 1. So here we have x and y-intercept 0, 0, and then x-intercept 4, 0. Okay, so that's our algebra, right? That's always 1. That's just the algebra part. Okay, step 2 is first derivative. Kind of categorize it like that. I think that helps. And then also, not only are you practicing graphing, but you're practicing your algebra, you're practicing your first derivative test, you're practicing second derivative with concavity. So these are really great problems to review with as well. So the first derivative, so if I rewrite y minus x, we have to go ahead and find that first derivative. That first derivative, and again, I can always rewrite this as 2 times x to the 1/2 minus x. And I hope you've memorized the derivative of x to the 1/2. We use that so much, right? 2 times x, 2 times 1/2, bring the power down, bring it down by 1, and then minus 1. And just rewriting it nicely, reducing out those 2's, we see that we get 1 over the square root of x minus 1. So that's the first derivative test. To find critical numbers, right, we have to set y prime equal to 0. So that means that we'll have 0 equal 1 over the square root of c. There we go. Minus 1. And I like rewriting critical numbers with C only because it stands for critical numbers, but also it differentiates from my domain, my X values. If I know it's, remember, not every C value is a local extreme value or a point of inflection, right? Every critical number that we get is not something we include into our information, right? Our behavior of the function. So we just have to make sure that we know the difference between critical numbers and local extrema. In this case, again, remember that critical numbers is y prime equals 0, but also where y prime is undefined. So we just need to be careful of those two pieces, right? So let's go ahead and add 1 to the right, and that's going to be equal to 1 over square root c. And doing some first derivative magic here, algebra magic here of solving, I'll do like a proportion, like a cross multiplication. So that way I get the square root of c is equal to 1. And therefore, this implies that c is equal to 1. Okay. So, and 1 is in the domain. Right? We have to make sure that it's in domain. And where is this undefined? Notice that this critical number is also undefined. So, okay, hold on. This is where y prime is equal to 0 and c equal to 0, and that is where y prime is undefined, right? If this is the derivative, I put a 0 in there, it's a goner, right? And it's also undefined everywhere, everything less than 0, right? Any negative number would make it imaginary. However, those numbers are not in the domain. Notice the original domain included 0 to infinity. So that means that since 0 is undefined here, which was included in the original domain, it makes it undefined there. So we have 2 critical numbers, and now we're on our way. All we have to do is test around them. Because of our domain is from 0 to infinity, we really aren't going to test anything to the left of 0 because nothing exists over there, right? So let's go ahead and finish this out, and I'm going to go in a column. I think that's a little more organized. I'll do my first derivative test, and I'll put, okay, that didn't work out well. There we go. 0 and then 1. And I usually draw these dashed and circled just because with all the test values, I'm like, which one was the critical? Which one was the not the test value, right? So I always say, okay, y prime is the sign of the value, and this is going to be the behavior of y. And then again, I'm not going to do anything to the left of 0 because the domain doesn't include anything left to the 0. So I don't have to worry about that. So let's just pick something in between here. I'll pick 0.5 and then maybe 2, like that. All right, so if I put in 0.5 into the first derivative, I get something positive, right? 1 over square root of 0.5. And then 1 over that would make it bigger than 1, and so it'll be positive. If I put in 2 there, same thing happens. I put in a 2 and then reverse, and then 1 over that minus 1 will leave it to be bigger than 1, so it'll be smaller than that small number minus 1 will give it a negative value. What does this mean to the original function? The original function means that it's increasing to the left in between 0 and 1 and decreasing on the right of 1. So this means at 1, we have a local maximum. All right, so we have all that first derivative stuff. Notice we don't have any local minimum, and we only have a local max, and we have increasing and decreasing intervals. So we have a local max at 1. And don't forget at 1, if we wanted to see the ordered pair, we just plug and chug back into the original function. So it'll be 1 comma, and then if I just put 1 here and 1 here, I'll get 2 minus 1, which is 1. So it's the 0.11 is my local max. There are no local min. And then we have increasing from 0 to 1 and decreasing from 1 to infinity. Okay, so all I have left now is second derivative. So now I have second derivative. So notice I just, again, I'm categorized, I'm very organized, right? I do algebra, first derivative, now second derivative. So I do know that my first derivative was 1 over the square root of x minus 1. And to find the second derivative, again, I'll just rewrite this as x to the negative 1/2 minus 1. And the reason why is that way we can take the power rule really quickly. So then we get the second derivative will be negative 1/2, drop it even further to negative 3/2. And then, of course, the constant's derivative is 0. And if I just rewrote this a little nicer, I would have negative 1 over 2 square root x cubed. And if I even wanted to be a little more fancy, right, I could have negative 1 over 2 and then x cubed, don't forget, is x squared times x. So square root of x squared, I can take out an x. Okay. So that's the second derivative. That's great. But really, what do I want? What do I need left is I need to determine if there are any points of inflection and if there's any intervals of concavity. So this means that I'm going to find the critical numbers of the first derivative. So let me write that. I'm going to find critical numbers of y prime, which means I need to find when y double prime is 0 or undefined. It's really important we understand that we're repeating this process of critical numbers, but again, only to the first and second derivative. So in order to do that, we have to set the second derivative equal to 0. So that'll be 0 equals negative 1 over 2. And then I'm going to put C for critical numbers. And then I'm going to go ahead and solve. Now, the fact that the numerator is where this function is 0, notice 0 does not equal negative 1. So this implies there are no values of C, no critical numbers such that y double prime is equal to 0. Okay, but we can see where it's undefined, right? Once again, it's undefined at 0. So we do know that there is a critical number C such that it's equal to 0 is where y double prime is undefined. However, we can only test, so when testing, okay, we'll put 0 here as the critical number, circle it. And once again, we'll test y double prime and then tell us the behavior of y, the original function. The domain of this function doesn't include anything to the left of 0, so we don't care. We only care what's happening on the right of 0. So we can pick something like maybe 2, I guess, right? So if I put 2 into the second derivative here, right? So negative 1 over a positive is just a negative number, which means to the original function. So if the second derivative is negative, that means the original function is concave down. It's really important we understand the difference between here and here. Here we only dealt with first derivative to determine intervals of increasing and decreasing and local extrema. When you get to the second derivative category, you use the second derivative to determine concavity and points of inflection. We can see now from our number line that we only have concavity down and no changes within concavity. So this means there are no points of inflection. But we do have concavity. So the concavity interval down is from 0 to infinity. However, there are no points of inflection and there are no intervals of concavity up. So let's go ahead and graph these. I like to graph them, see, at 0, 0, 4, 0, and 1, 1, like that. Then I go back to the thinner one. I do know it starts at 0. I do know that it's increasing from 0 to 1, right? And then decreasing and always concave down. So it's going to be concave down everywhere, but increasing to the left of 1 and decreasing to the right. So we can already see what that looks like. So let me go ahead and get that pen out. Just like that. And if I wanted to label, I can label, that too. As long as the points are there and they're accurate, I think it's fine. I think it's when we get into decimals, it's kind of hard to tell. But here, this is the process. The process will never change. The first part is always the algebra, whatever that entails. First derivative is second, and then the second derivative. And then there you can sketch and verify results. Of course, always use technology to always support your results.